So the balanced chemical equation for fossil fuel combustion is going to give us the exact relationship between the amount of fossil fuel that's burned and the amount of carbon dioxide that's given off. But fossil fuels are not a single compound. They are mixtures of compounds, and so this is the first of many approximations that we have to make in order to do this calculation. We're going to use octane as a representative fossil fuel. So this is octane, and when it burns, 2 moles, so this is octane, and when octane burns, 2 molecules of octane react with 25 molecules of oxygen. They form 16 molecules of CO2 and 18 molecules of H2O. So that's what the chemical equation is telling us. We can also interpret the chemical equation in terms of moles, because that's just multiplying all of the amounts by the same number. It's like dozens, right? If you have a dozen wagon frames and 4 dozen wheels, you have the ingredients to make a dozen wagons, right? 1 wagon body and 4 wheels, a dozen and 4 dozen. Just change the counting unit. So when we see a chemical equation, we usually use moles because that's a more reasonable amount. So just think of the unit mole being stuck in there. So 2 moles of octane react with 25 moles of oxygen to form 16 moles of CO2 and 18 moles of water. These coefficients give us relative amounts in moles, not in masses. It's in moles, because we're looking at the individual Lego blocks, the individual molecules, and how the atoms come apart. And then we're just scaling up with the unit mole.
So when we look at that, is it going, how are we telling that we're looking at that in moles?
That's a good question. How do we know to look at that in moles instead of molecules? It represents both. You use the one that's appropriate for your situation. You could do it in terms of dozens or a gross or a ream or any other counting unit, but those are just not useful in chemistry. So it does both at the same time. Having issues. Okay. So the amount of every substance that's used and the amount of every substance that's made in a chemical reaction, these are all related to each other. So we have the law of conservation of mass, which states that matter cannot be created or destroyed. And we balance the equations by balancing the atoms. And so how much product we get is directly related to how much reactant we start with. And the study of these numerical relationships is called stoichiometry. I'm not going to test you on that word, but you'll hear it tossed around, stoichiometry. So let's talk about pizza. A recipe is a little bit like a chemical equation. So here we have a very simple recipe for pizza. 1 crust, 5 ounces of tomato sauce, and 2 cups of cheese. Put those together, that'll make 1 pizza. This gives us the relationships between the quantities, right? So we can say that there's a ratio of 1 crust to 5 ounces of sauce to 2 cups of cheese to 1 pizza. And so we can use this to say, well, if I have 10 cups of cheese, how many pizzas could I make? 5. And we can do that in our heads because it makes sense to us, right? We're doing the same thing with a chemical reaction, but we can't just reason it out, so we need to be able to write it out and get the units to tell us what to do. So for this one, starting with 10 cups of cheese, I can convert between any reactant and another reactant or any product. I can pick any 2 pieces of this and get a relationship between them. So here I've got cups of cheese and I want pizzas. So I can do this in just one step. I'm going to go to pizza as the unit, and I'm going to divide by cups of cheese. So those cancel out. And then the ratio here comes from the coefficients. There's one pizza from every 2 cups of cheese. One pizza from every 2 cups of cheese. 10 divided by 2, 5 pizzas. That's what you did in your head when you said, oh, you can make 5 pizzas. Any questions? So the ratios of coefficients in a chemical equation act as conversion factors between amounts of reactants and products in moles. And we can look at any 2 of the terms. So we don't have to, if we want water, we don't have to start here and go through all of them. We can go directly from octane to water. We know the relationship between these 2, between these 2, between those 2, any 2. Just pick them, and we have the relationship. So if we burn 22 moles of octane, so 22.0 moles of C8H18, how many moles of CO2 form? So we want to know moles of CO2. I want to divide then by moles of C8H18. So the units come out. Stoichiometry is one of the biggest reasons why learning dimensional analysis is really important. I put the units in. Now I go looking for numbers, and I see that there's a 16 in front of CO2. That means 16 moles of CO2. So in front of moles of CO2, I'm going to write 16. Down here, I've got C8H18, so I look for the coefficient in front of that in the formula, and that's what I write down here. I could simplify that to 8, but I don't see the point, because sometimes when we do mental math, we screw it up, right? Just take 22 times 16 divided by 2. 176. Moles of CO2. And should have 3 sig figs, so there we go. Any questions? The balanced chemical equation gives us relationships in moles between the compounds. But we measure things in grams. So we need to convert from our measurement in grams to moles, and then use the mole ratio from the equation to get to moles of the thing we're interested in, and then we have to convert back to grams because that's more meaningful. And so this is the basic conceptual plan for stoichiometry: the mass of A to the amount of A in moles to the amount of B in moles to the mass of B. And so I call this grams to moles to moles to grams. In chapter 3, we learned how to convert between grams and moles, the molar mass of the element or the compound, right? And here's another mole to gram. Again, that's the molar mass. That's chapter 3 stuff. This part in the middle is what we just learned today, converting from moles of one thing into moles of another thing, and it's just the coefficients from the equation. So this is the starting point for all stoichiometry problems. And then sometimes we need to modify it. We're going to learn some variations on this, but you start here. Grams to moles to moles to grams. Grams to moles to moles to grams. You should wake up in the middle of the night muttering grams to moles to moles to grams. And then you know that it's really getting into your head, because that's the starting point. So the hardest part of most of these problems is figuring out the path. And here I'm telling you, this is a path to start with. You might need to tweak it a little bit, but here's where you start. Grams to moles to moles to grams. So let's do an example. Back to the CO2 thing. So according to the U.S. Department of Energy, the world burned 3.3 times 10 to the 10th barrels of petroleum in 2013, the equivalent of approximately 3.7 times 10 to the 15th grams of gasoline. Calculate the mass of CO2 emitted into the atmosphere using the combustion of octane as the representative equation. Do you see how many approximations are in this? So the Department of Energy says the world burned 3.3 times 10 to the 10th barrels of petroleum. Is that an exact number? Heck no. It's got two significant figures for a reason and a whole bunch of zeros after that. That's an estimate. And then we say that's approximately equivalent to this many grams of gasoline, because that was barrels of petroleum and they were approximating it in gasoline. So there's another approximation. So are we going to end up with a really firm number of how much CO2 was emitted by human combustion of fossil fuels? No. But we're going to get an idea, like a ballpark figure. So we've got our balanced chemical equation, and I like to use that to organize the information. Because again, these are dimensional analysis problems, and so we have to figure out what am I given, where am I starting, and where am I trying to go. So this one is more of a story problem, and so the barrels of petroleum, that's sort of background info. This is the mass that we're starting, and it says mass of gasoline, but we're going to pretend that it's octane. So this one's a little bit confusing interpreting what those things say. But we're going to take that to mean 3.7 times 10 to the 15th grams of octane. So I'm going to write that number under, I'm going to try to write that number under, can't talk at the same time, under the formula. And then what am I trying to find? The mass of CO2. So here's CO2. So this is what I'm trying to find. This is what I don't know. I'm going to put a question mark there. And it says the mass. Well, what would be an easy unit? Grams? So I'm going to find grams of that. So this tells me what I'm starting with and what I'm ending up with. And what's the path? Grams to moles to moles to grams. So in these earlier ones, I'm going to write that out. So we're going to start with 3.7 times 10 to the 15th grams of C8, H18. Grams to moles. So I'm going to convert that to moles of C8, H18. Grams to moles of the thing I want. I'm going to completely ignore these other things. I'm only interested in CO2. So I'm going to convert this to moles of CO2. Grams to moles to grams. In each of these steps, one thing is changing. In the first step, we're changing from grams to moles, but we're talking about the same compound. In the last step, we're changing from moles to grams, but again, we're talking about the same compound. In the middle, we've got the same unit, different compounds. You can only change one thing at a time. It's like 7 steps from Kevin Bacon, right? So now that I have this, we just follow the pattern for dimensional analysis. I have 3 arrows. I'm going to have 3 fractions. 3.7 times 10 to the 15 grams of C8H18. And it's important to write down grams of what here. You can't just skip out on those formulas. Times and a line, and this line's going to have moles of C8H18 on it. And then another line to go to moles of CO2. And then the last one is going to be grams of CO2. Grams to moles to moles to grams. I take the previous unit and put it in the denominator because I need those to cancel out. And then down here, canceling out. canceling out. All the units in place. The units then tell me where to put the numbers, and I really don't have to think about it. I like doing the one in the middle first because I can just pull the numbers out of the equation. I don't have to calculate anything. I'm looking for the ratio between moles of CO2 and moles of C8H18. So I look at the balanced chemical equation, and I say, well, what number is in front of CO2? 16. So that represents 16 moles of CO2. And that's coming from 2 moles of octane. And I stuck that in the wrong place. It's supposed to be over here. 2 moles of octane. Again, you could simplify it, but why? Just leave it alone. How do I convert from grams to moles of octane? I need the molar mass, right? So I'm going to have to calculate that. We do a lot of calculating molar masses. So I have 8 carbons times 12.01 and 18 hydrogens times 1.008. Getting 114.224. Correct me if I'm wrong. So that's the grams, the mass of 1 mole of octane. I'm going to put that in here. And then at the other end, I need the molar mass of carbon dioxide. So there's 1 carbon and 2 oxygens. And so that's 44.01. 1 mole of CO2 weighs 44.01 grams. Any questions? There's my equation. Start at the left and go across to the right. Multiply by the top, divide by the bottom. So 3.7, and as I press the EE button, I think times 10 to the 3.7 EE 15. And I'm going to divide by 114.224, and I'm going to multiply by 16 and divide by 2 and multiply by 44.01 equals. And as I'm writing this down, I'm going to think, well, how many significant figures am I going to need here? Well, the starting number only had 2. So the ones in the middle had more, so this is only going to have 2. And then look all the way to the end of that number. There's a times 10 to the 16. You don't want to forget that. So this is going to come out to be 1.1 times 10 to the 16 grams of CO2. These numbers in the middle, 16 to 2, those are exact numbers, because exactly 2 molecules will react and form exactly 16 molecules. Any questions? So that sounds like a lot of CO2. Let's compare that to how much volcanoes produce. So this is what we just calculated, 1.1 times 10 to the 16th grams of CO2 per year. And there's no reference given, but somewhere they've got this estimate that volcanoes produce about 2 times 10 to the 14th grams of CO2 per year. So that's smaller. Is it significantly smaller? Well, why don't we find out how many times smaller it is? Let's take the big one and divide by the small one. So 1.1 times 10 to the 16th grams per year. That's not a very good 6. Divided by 2 times 10 to the 14th grams per year. And And my calculator says 55. Which, one significant figure, I guess you'd have to round that to 60. But. So petroleum combustion produces 55 times more CO2 than volcanoes. So volcanoes are probably not responsible for the increase in CO2. Does this conclusively prove that fossil fuel combustion is? No, it doesn't. It suggests, but it doesn't prove anything. Any questions? Let's do another example. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, primarily HCl, according to the reaction. What mass of HCl in grams is neutralized by a dose of milk of magnesia containing 3.26 grams of magnesium hydroxide? So there's our balanced chemical equation. And the part at the top is this background story. The line below is what we really need to do. So I've got 3.26 grams of MgOH2. So I'm going to find that in the formula, and I'm going to write the amount underneath. 3.26 grams. And then it's asking me what mass of HCl in grams. So I find where's HCl? Well, HCl is the other reactant. So this is what I'm trying to find, question mark, grams. Here I've got two reactants. In the previous problems, I had one reactant and one product. It can be any combination. So what's the path? Grams to moles to moles to grams, right? I'm going to write it up on the top. So grams of what I'm given, magnesium hydroxide, to moles of magnesium hydroxide, to moles of what I'm interested in, to grams. Grams to moles to grams. Write out the path. Then I can make my equation from that, putting in units first. So I've got my 3.26 grams of magnesium hydroxide. I got 3 arrows. It's very common. So 3 lines. Grams to moles to grams. Grams of magnesium hydroxide to moles of magnesium hydroxide. To moles of HCl to grams of HCl. Then I'm going to put grams of MgOH2 down here, so those units cancel out. And moles of MgOH2 down there, so they cancel out. I would recommend leaving yourself more room than I left myself here. Sometimes it's helpful to take a piece of notebook paper and turn it sideways so that you can write a longer equation, because it gets confusing when you have to wrap around onto another line. All my units are in place. The one in the middle is my mole-to-mole ratio, and that comes from the balanced chemical equation. In front of magnesium hydroxide, there's nothing. That's a 1, right? And so down here, I can put a 1 there, or I could leave it blank. That's a 1. And how many moles of HCl? 2. And then I need some molar masses. And one of the ways we make these problems a little faster on an exam is we give you the molar masses so that you don't have to calculate those on the side. But we're still practicing. So 24.5, well, 24.31, that was close. Magnesium. And then the OH in parentheses means I've got 2 of those units. So I've got 2 oxygens and 2 hydrogens. And 24.31 plus 2 times 16 plus 2 times 1.008. 58.326. So 1 mole of magnesium hydroxide weighs 58.326 grams. And then for HCl, the mass of hydrogen plus the mass of chlorine. $36.458. 1 mole weighs 36.458 grams. We got grams to moles to moles to grams. I put the units in, and then the units tell me where to put the numbers. I don't have to think, well, I'm supposed to divide by the molar mass of the first one and multiply by the mass of the, no, just let the units tell you what to do. Okay, so now we calculate 3.26 divided by 58.326 times 2 times 36.458. And thinking about significant figures, I'm starting with 3, and everything in the middle has 4 or more. So this is going to be 4.0754 grams, which is going to be 4.08 grams of HCl. Any questions? I think we got one more example, and we'll be done for the day. 4.08 up in the corner. More story here. A component of acid rain is nitric acid, which forms when NO2, a pollutant, reacts with oxygen and water according to the simplified equation given here. The generation of the electricity used by a medium-sized home produces about 16 kilograms of NO2 per year. Assuming that there's adequate O2 and H2O, what mass of HNO3 in kilograms can form from this amount of NO2 pollutant? This is one of the things that contributes to acid, well, it says that, acid rain, yeah. Well, there's all this story in here, but what am I given? There's only one number in there, 16 kilograms of NO2. So 16 kilograms of NO2. And they're saying what mass of HNO3, so over here HNO3 is the product this time, question mark, they're saying they want it in kilograms. So what's the path we start with? Grams to moles to moles to grams. Grams to moles to grams. Is it going to work just like that? No, because we're starting with kilograms and we're ending with kilograms. So we could add a term on the beginning, kilograms to grams, to moles to grams to kilograms. And this is where I have to make a decision, because there are like 3 pretty good ways of dealing with that kilogram business. You can just convert the kilograms to grams and then use regular grams to moles to grams. You can do this whole path with the extra terms at each end, or you can do grams to moles to grams and just not cancel out the kilogram. Anybody have an opinion of which one you want to see? One's tedious but very straightforward. Another one's multiple steps, and then one's kind of tricky but sometimes confusing. Not going to help me out?
So if we do the one where we just don't cancel out the kilograms,
Mm-hmm.
we're just using
Yeah, well, let's do that one. So 16 kilograms is what I'm starting with. What I'm going to do is I'm going to write the kilo in red. What does that mean, the kilo? It means 1,000 times 10 to the 3. So if I wrote 16 times 10 to the 3, that would be the same, right? Now, if I was using 16 times 10 to the 3, would I have to cancel out the 10 to the 3 when I do the math? No, I would just cancel the gram, right? And this could just be part of the number. So what I'm going to do here is I'm going to leave the kilo there. I'm going to cancel grams. And I'm going to go to moles, and then back to grams. And the kilo is still going to be there, and so my answer is going to be in kilograms at the end. So this is kilograms of NO2. And I'm going to go to moles of NO2. Oops. And then moles of HNO3. And then grams of HNO3. So I'm going to put grams of NO2 down here. That cancels out the grams, but not the kilo. And so if we're looking at this alternate one down here, what I'm canceling out is the grams of NO2. There's moles of NO2, and those are going to cancel. And moles of HNO3. So my mole ratio in the middle, what do I write in front of HNO3? 4. And what do I write in front of moles of NO2? Also 4. They're both 4. I need the molar mass of NO2, mass of nitrogen, 2 times the mass of oxygen, is 46.01. So 1 mole of NO2 is 46.01 grams. And then molar mass of nitric acid, I don't remember that one. .018. So if I do the 16 divided by 46.01 times 4 divided by 4 times 63.018 equals, and 2 sig figs, 21.91 grams, and I didn't cancel out the kilos, so that's still there. 2 sig figs, that would round to 22 kilograms. What if I use this one instead? So that's not standard notation, standard scientific notation. Your calculator doesn't care. You can punch it in like that. 16 EE3 divided by 46.01 times 4 over 4 times 63.018 equals. This is going to give me 21 914 grams, 21,000. And then how do I make that into kilograms? I need to factor out 10 to the 3, right? So that's 22,000 grams, or 22 times 10 to the third grams, which is 22 kilograms. Same thing. Any questions?